It's the summer of 55 BC. Julius Caesar is standing on the west bank of the Rhine River, looking across 400 yards of fast-moving, ice-cold water. On the other side, Germanic tribes who have just been raiding Roman-controlled territory, then skipping back across the river like they know Rome can't follow. They know no army has ever crossed the Rhine under arms. They know the river is their shield. Caesar doesn't call for boats. He doesn't look for a ford. He doesn't redirect his campaign around the obstacle. He turns to his engineers and says, "Build me a bridge, not a rope crossing, not a raft, a full military bridge, wide enough for legions to march across 4 abreast, strong enough to carry siege equipment, built across a river that runs 30 feet deep in places, and with a current that would rip apart most wooden structures within hours." And his engineers said, "Yes, sir. Give us 10 days. 10 days later, 40,000 Roman soldiers walked across a wooden bridge spanning the Rhine, a river that the Germanic tribes had considered an uncrossable border, a natural guarantee of their safety from Rome. The tribes on the far bank didn't fight. They abandoned their villages and fled into the forests, genuinely terrified, not by the soldiers, by the bridge. After spending 18 days on the German side, burning villages, receiving submissions, and demonstrating Roman power, Caesar ended the campaign on his own terms. Once satisfied with the psychological impact, he ordered his engineers to dismantle the bridge. Not because it was falling apart. Not because he needed the timber, but because he wanted the Germans to understand something that no battle could have communicated as clearly. Rome could do this whenever it wanted. The Rhine was not a boundary, it was just a river. That bridge existed for 18 days. It took 10 days to build. 2,000 years later, engineers at MIT, Berkeley, and universities across Europe are still trying to understand the full extent of what Rome's builders could do, and in several critical areas, still cannot replicate it. This is the story of how Rome was built. Not the pretty monuments in your travel photos, but the system, the speed, the materials, science, and the organizational genius that let a civilization without power tools or computers construct things that still embarrass modern construction timelines. And fair warning, by the end of this video, but you will never look at the Pantheon the same way again. Before we examine specific Roman buildings and bridges, we should first address a common misunderstanding about Roman engineering. Most people look at Roman monuments, aqueducts, the Colosseum, and roads, and ask, how did they build so much without modern machines? That's the wrong question. The right question is, how did they build a system that could produce all of that consistently across an empire spanning from Scotland to Iraq for 500 years? Because the secret to Roman construction speed wasn't a single invention. It wasn't just the concrete, as remarkable as that material is. It was something more fundamental. Roman industrialized construction occurred before the Industrial Revolution. They built an organizational machine, and that machine is what made everything else possible. Start with the army. In every civilization before Rome, armies fought and construction workers built. They were separate professions, separate labor pools, separate knowledge bases. Rome collapsed that distinction. The Roman legion was simultaneously the ancient world's most effective fighting force and its most sophisticated engineering corps. When legions weren't actively on campaign, they built roads, bridges, fortifications, supply depots, and aqueducts. This wasn't busy work to keep soldiers out of trouble, although that was a side benefit that Augustus explicitly appreciated. It was structural. Engineering skills were baked into military training. A Roman legionary could survey a road, grade an embankment, drive timber piles into a riverbed, and mix mortar, and with the same institutional competence he brought to a shield wall. What this meant in practice was staggering. When Caesar needed that Rhine bridge, he didn't have to locate a civilian construction firm. negotiate a contract, wait for materials procurement, or manage a workforce that had never operated under military discipline. His 40,000 soldiers were the construction firm. They had the tools, the training, the timber procurement knowledge, and the command structure to execute immediately. No approvals process, no subcontractor coordination, no budget committee. Now extend that logic across an entire empire and 5 centuries. Every legion posted on every frontier was also a construction unit. The roads, forts, and aqueducts that spread Roman infrastructure from the Sahara to Hadrian's Wall weren't built by separate civil engineering agencies. They were built by soldiers who happened to also know how to fight. That integration of military and engineering capability is something no modern nation has fully replicated at Roman scale. But there's a second piece, and this one is almost more impressive: standardization. Rome figured out something that modern manufacturing would spend the 18th and 19th centuries rediscovering. If you want to build fast across a massive geographic area, you need standard parts, standard procedures, standard specifications that can be handed to any team anywhere and produce the same result. Roman roads are the clearest example. The width was standardized. As the layer sequence was standardized: trench to bedrock, large foundation stones, crushed rubble, concrete layer, surface paving. The drainage profile was standardized. The milestone markers placed every Roman mile, inscribed with distance, the name of the reigning emperor, and the name of the official responsible for that section, were standardized in height, diameter, and weight. This meant a road crew deployed from Rome to Britain wasn't starting from scratch, figuring out how to build a road in a foreign environment. They were executing a known procedure with known materials on known timelines. The cognitive overhead was minimal. The execution speed was maximum. And it wasn't just roads. Brick sizes were standardized across the empire, which meant supply chains could run efficiently between regions. And arch proportions were standardized, which meant any trained mason could build to spec without a master architect standing over his shoulder. Aqueduct channel dimensions were standardized, which meant maintenance crews from one province could service infrastructure built by engineers from another. This is the Roman construction machine, a military labor force with built-in engineering competence, executing standardized designs with standardized materials under centralized command authority. No bidding process, no permitting delays, no jurisdictional conflicts between city, regional, and imperial bureaucracies. The emperor wanted a road built from point A to point B. The emperor's proconsul directed the nearest legions. The legion's engineers surveyed the route. The legion's soldiers dug and laid. Or the milestones went up with the emperor's name on them as a reminder of who made it happen. Accountability ran in one direction, from emperor to general to centurion to soldier, with no friction points in between. In modern infrastructure project management, you would call this single-source accountability with full vertical integration of design and construction. In ancient Rome, they just called it Tuesday. Now, all of this organizational genius would have been significantly less impressive if the Romans had been stuck with ordinary building materials. But they weren't. Because somewhere around the 3rd century BC, Roman builders discovered something in the volcanic soils around Naples that would change architecture forever. And it has a chemistry that science only fully decoded in 2023. Let's talk about the concrete. And let me start with what Roman concrete is not, because most people have the wrong mental image. It is not the gray sludge that gets poured out of a mixer truck on a modern construction site. It is not Portland cement. It doesn't look like it, work like it, or behave like it. Calling Roman concrete concrete is a little like calling a Damascus steel sword a knife. Technically accurate, catastrophically undersells what it actually is. The Romans called it opus cementitium, and its core ingredients were volcanic ash, lime, seawater, and rubble aggregate. Simple list. Profound chemistry. The volcanic ash, called pozzolana, named after Pozzuoli near Naples, where the best deposits were found, was the key. When it reacts with lime and water, it produces chemical compounds that are fundamentally different from what modern Portland cement produces. The Romans documented this in obsessive detail. Vitruvius, writing around 25 BC in his 10 books on architecture, specified the exact ratios: 1 part lime to 3 parts pozzolana for structural buildings, 1 part lime to 2 parts pozzolana for underwater construction. He noted specifically that when pozzolana is mixed with lime, it hardens not just in air but underwater, and called this extraordinary. He had no idea how extraordinary. Nobody did, for 2,000 years. Here is what was actually happening at the molecular level, which took modern materials scientists until relatively recently to fully understand. The volcanic ash contains reactive silica and alumina. When those compounds mix with lime and water, they don't just solidify, they trigger a cascading series of chemical reactions that produce extremely durable crystalline structures, calcium-aluminum silicate hydrates, that continue developing and strengthening for years, decades, even centuries after the initial pour. Modern Portland cement works differently. It cures fast, reaching most of its structural strength within 28 days, and then the chemistry largely stops. This is perfect for modern construction finance, which runs on tight schedules and borrowed money. But it means your concrete is essentially done growing at 1 month old. It won't get stronger. From that point forward, it only degrades. Roman concrete, by contrast, cured slowly. Months, sometimes years. The chemistry kept running. The crystalline structures kept developing. In some environments, particularly marine environments, the Romans' concrete kept getting stronger for centuries after it was poured. I need to stop for a second here, because I know how that sounds. I want to be precise. This is not mythology, or the kind of enthusiastic ancient history overstatement that history channels sometimes traffic in. This is peer-reviewed materials science. And the 2023 study from MIT is where it gets genuinely jaw-dropping. For a long time, archaeologists and materials scientists had noticed something in Roman concrete samples that looked like a sloppy construction technique. Small white chunks embedded in the concrete matrix, chunks of unmixed lime that, by modern standards, should not be there. If you're making concrete and you have clumps of unreacted lime in your mix, that's a sign you didn't mix properly. At bad quality control. Admir Masick at MIT started asking a different question. He said, "The Romans put tremendous effort into documenting and perfecting their construction materials across centuries of empirical refinement. Why would they be so careless about this one thing? There has to be more to the story." What his team discovered, using advanced microscopy and chemical analysis, is that those lime clumps, which they call lime clasts, are not evidence of poor technique. They are a deliberate feature of a process called hot mixing. Instead of using slaked lime, which is lime that has already reacted with water and cooled down, the Romans appear to have mixed quicklime, raw, freshly burned limestone, directly into the aggregate while it was still hot. This created extremely high temperatures during the initial mix. And those high temperatures produce chemical structures in the lime clasts that are different from anything slaked lime can produce. Specifically, a brittle, porous, highly reactive calcium structure that behaves in a remarkable way when the concrete is later stressed. When a microcrack forms in Roman concrete, as eventually happens in any material, water seeps in. The water dissolves calcium from the lime clasts. That calcium-rich solution then migrates to the crack face and recrystallizes as calcium carbonate, sealing the crack. Automatically, with no human intervention, Roman concrete heals itself. And the hot mixing also accelerated curing. Massic's team notes it significantly reduces curing and setting times, meaning Rome got both speed benefits during construction and longevity benefits over the long term, more from a single material system. Now add the marine environment, where the chemistry gets even stranger. When Roman concrete was poured in seawater, in harbor walls, pier foundations, coastal retaining structures, the seawater begins to slowly percolate through the matrix over decades and centuries. The seawater reacts with volcanic minerals in the aggregate, particularly philipsite, and produces a new crystalline structure called aluminous tobermarite. These tobermarite crystals grow slowly inside the concrete, filling microscopic voids, interlocking with the existing structure, literally reinforcing the material from the inside out. Modern concrete exposed to saltwater corrodes. The salt attacks the steel rebar that holds it in tension. The rebar expands as it rusts, and the concrete cracks from the inside. Seawall sections built in the 1970s are already crumbling. Modern harbor infrastructure needs complete replacement every 30 to 50 years. Roman harbor concrete at Caesarea Maritima in Israel, built between 22 and 15 BC by Herod the Great using volcanic ash imported from Puteoli in Italy, is still structurally sound. 2,000 years later, in the Mediterranean seawater that has been attacking it every day since Augustus was emperor. Pliny the Elder, writing in the 1st century AD, described Roman marine concrete as a single stone mass, impregnable to the waves, and every day stronger. Modern scientists initially assumed this was ancient hyperbole. It turns out Pliny was describing an actual material phenomenon, even if he couldn't explain the chemistry. So why don't we build with Roman concrete today? Or this is the question I get every time I cover this topic, and the answer is both practical and somewhat damning about modern construction priorities. The answer is speed. Portland cement reaches working structural strength in 28 days. Roman concrete took months to years to reach its maximum strength. Modern construction projects are financed by loans with interest charges that accumulate daily. Every additional week, a structure takes to reach load-bearing capacity costs real money. The economics of modern construction demand fast-curing materials, and we've optimized our entire industry around that demand at the expense of long-term durability. There's also the supply chain problem. Pozzolana, the specific volcanic ash that gives Roman marine concrete its extraordinary properties, is geographically limited. The high-quality deposits near Pozzuoli in Italy aren't available in unlimited quantities globally. Building a global supply chain for them comparable to the existing Portland cement industry is a decades-long project. The deeper irony is this. We have optimized for building fast with materials that fail in 50 to 100 years, while Rome optimized for building slower with materials that last millennia. The math on which approach is actually more efficient over any reasonable long-term horizon is not flattering to the modern construction industry. Research teams are currently working on replicating Roman concrete formulations for use in coastal infrastructure, precisely because climate change is accelerating the rate at which modern seawalls and harbor structures are failing. The ancient solution, 2,000 years old, may end up being the answer to a 21st century engineering problem. I want to tell you a number, and I want you to really hear it. 43.3 meters. That is the diameter of the Pantheon's dome. It is also precisely the height from the floor to the center of the oculus at the top. The interior of the Pantheon is proportioned so that a perfect sphere 43.3 meters in diameter would fit exactly inside it, touching the floor and the top of the dome simultaneously. The Romans did this deliberately, as a mathematical and philosophical statement about the perfection of the celestial sphere. Now here is the number I really want you to hear. This dome was completed around 126 AD. It has been standing continuously since then, through the fall of the Western Roman Empire, through the medieval period, more through earthquakes and floods, and centuries of neglect, and more than a few attempts to strip useful materials off of it. One Byzantine emperor in the 7th century removed the gilded bronze roof tiles and shipped them to Constantinople. The dome survived. In 1625, Pope Urban VIII famously melted down all the remaining bronze from the portico ceiling to make cannons, an act that Roman citizens called "what the barbarians didn't do, Barberini did." The dome survived. It still holds the world record for the largest unreinforced concrete dome ever built. After 1900 years, no one has built a larger one from concrete alone, without steel reinforcement. When Michelangelo first saw the Pantheon in the early 16th century, he looked at it for a long time and then said it was of angelic and not human design. That's a remarkable statement from a man who designed the dome of St. Peter's Basilica, which, for the record, has a diameter of 136 feet. The Pantheon's dome is 142 feet. Let me walk you through exactly why this dome works, because the engineering is astonishing when you understand what problem the Romans were solving. Building a dome is fundamentally a problem of managing two competing forces. A dome works in compression along its meridional lines, the lines that run from the base to the apex, like the seams of an orange, meaning those sections of the dome are being squeezed together, which concrete and stone handle well. But at the base of the dome, or there are circumferential or hoop stresses that are tensile. The dome is trying to spread outward at the bottom, which wants to pull the material apart. Concrete and unreinforced stone are weak in tension. That's why modern domes use steel rebar to handle the tensile stresses that unreinforced concrete can't manage. The Romans had no steel rebar, and they built the largest such dome in history anyway. How? They engineered around the material's weaknesses with three simultaneous strategies that together produce a structural system more sophisticated than the bare numbers suggest. The first strategy is what I think of as the gradient aggregate system, and it is genuinely brilliant. As you move up the dome from base to apex, the concrete mixture changes. At the base, it's where compressive loads are highest and structural robustness is most critical. The aggregate is travertine limestone, one of the densest, heaviest, most compressive strength-capable materials available. As you move upward, the aggregate progressively transitions, first to brick fragments and tufa, then to lighter porous volcanic scoria, then to light tufa and pumice near the oculus. At the very top, near the oculus, there are hollow clay pots embedded in the concrete, literally creating air pockets to reduce weight at the most critical load point. The dome's thickness also changes, from 5.9 meters at the base to 1.2 meters at the oculus ring. The result is a structure that is simultaneously massive and light in exactly the right proportions to manage the stress distribution throughout. And the Romans had no finite element analysis software, no structural engineering degree programs. What they had was centuries of accumulated empirical knowledge. Build it, watch it, learn from what cracks and what doesn't, refine the recipe, pass the knowledge to the next generation of engineers. Vitruvius documented the principles. Emperor Hadrian's builders executed them. When modern engineers run finite element models of the Pantheon's dome today, they find that the maximum tensile stress in the structure is only about 0.13 megapascals, well within what Roman concrete can handle without cracking. This was not an accident. The second strategy is the oculus, and I think people consistently underestimate how important it is structurally. The 8.7-meter circular opening at the top of the dome is not an aesthetic gesture, although it creates one of the most extraordinary interior light effects in the history of architecture. A cylinder of sunlight that tracks across the interior over the course of the day like a natural sundial. Structurally, the oculus is a load relief valve. The apex of a hemispherical dome is where tensile hoop stresses are most concentrated. Without the oculus, the 4,535-ton weight of the dome would be trying to pull apart the concrete at exactly the point where it is most vulnerable. The oculus removes material at that critical point, relieving the tensile stress. And the ring of concrete around the oculus acts as a compression ring, concentrating the dome's loads into a circular band that the material handles very well. The 4,535 tons of dome weight is channeled through the oculus ring, and through the stepped exterior rings visible on the outside of the dome, and down into the 6-meter-thick rotunda walls. It is an extraordinarily efficient load path for a completely passive structural system. The third strategy is the coffers, the 140 square recesses arranged in 5 rings inside the dome, each ring of coffers getting smaller as they approach the oculus. They look decorative. They are decorative. But they're not only decorative. Each coffer removes mass from the dome at carefully chosen locations, reducing overall dead load. Modern analysis shows they contribute a relatively modest reduction in total weight, less than 5%, but they do so at geometrically important positions in the stress distribution. The Pantheon has stood through earthquakes, floods, fires in the city, but complete neglect for centuries during the medieval period, and heavy tourist traffic for the last 500 years. It's the most visited historical site in Italy, drawing over 9 million visitors in 2019 alone. It is also still a functioning church. It has been used continuously as a place of worship since 609 AD, making it quite possibly the oldest building in the world that has never stopped being used for its intended purpose. The United States Capitol Dome, for reference, is 96 feet in diameter, completed in 1863, and is made of cast iron. The Pantheon's dome is 142 feet in diameter, completed around 126 AD, and is made of concrete that has been healing its own micro-cracks for 19 centuries. I'll let you sit with that comparison for a moment. Here is a comparison that I find both impressive and slightly embarrassing, depending on which side of it you're on. The Roman Colosseum. Construction began in approximately 72 AD under Emperor Vespasian. It opened in 80 AD under his son, Titus. That's roughly 8 years to build an elliptical amphitheater 189 meters long, 156 meters wide, and 48.5 meters tall, with seating for between 50,000 and 80,000 spectators, 80 arched entrances at ground level, and a complex underground system of tunnels, animal pens, and mechanical lifts. The new Wembley Stadium in London. Construction began in 2002, opened in 2007. That's 5 years for a 90,000-seat stadium using modern steel construction, computer-aided design, and a full suite of 21st-century construction equipment. Wembley also cost around £798 million and went $300 million over budget. I'm not saying Rome was faster than modern construction in every case. I'm saying the comparison is a lot less comfortable for the modern side than most people expect. The outer wall of the Colosseum required over 100,000 cubic meters of travertine limestone. The stones were quarried at Tivoli, 20 miles northeast of Rome, and transported on a dedicated supply road that was upgraded specifically for the project. They were held together not with mortar, but with approximately 300 tons of iron clamps fitted into precisely cut sockets in the stone faces, a connection system that requires extremely accurate stone cutting but eliminates the curing time of mortar entirely. Inside the travertine facade, the structural core of the Colosseum is predominantly concrete, and the Romans used different concrete mixes for different elements: heavier, denser mixes for load-bearing piers, lighter volcanic tuff aggregate for the vaulted sections, where reducing dead load mattered. The system of vaulting is what makes the whole thing work. The Colosseum's structure is essentially a matrix of radial and concentric barrel vaults, stone and concrete arches running in two directions simultaneously, distributing the enormous loads from 80,000 spectators through an efficient series of compression paths down to the foundations. Here is where the speed story gets really interesting. Historians analyzing the Colosseum's construction believe the Romans divided the project into 4 quadrants, effectively 4 independent construction zones, each managed by a separate contractor, each with its own workforce and supply chain, all building simultaneously to identical specifications. The seams where the quadrants meet are nearly invisible today. The standardization was good enough that 4 independent teams working simultaneously produced a structure with no visible discontinuities. This is parallel processing. In modern construction scheduling, it's called fast-track construction, and it's considered an advanced project management technique. Rome was using it on the scale of the largest amphitheater in the ancient world in the 1st century AD. The supply road from Tivoli's quarries was not just a road. It was a dedicated high-capacity transport corridor, upgraded specifically to handle the volume of travertine the Colosseum required. This is infrastructure built to serve other infrastructure. The Romans invested in their supply chains the way a modern construction firm would invest in logistics planning, because they understood that material delay is construction delay. The workforce itself was a mix of skilled professional builders, engineers, surveyors, master masons, architects, specialized craftsmen, and an estimated 60,000 to 100,000 Jewish captives brought to Rome after Titus's victory in the First Jewish-Roman War and the destruction of Jerusalem in 70 AD. The entire project was explicitly funded by the looted treasury of the Second Temple. An inscription found at the Colosseum site reads, "The Emperor Vespasian ordered this new amphitheater to be erected from his general's share of the booty." This is worth sitting with for a moment, because it is both an engineering and a moral story, where the speed of Roman construction was partly a function of organizational excellence and materials science genius, but it was also partly a function of access to coerced labor at a scale that modern construction simply does not and cannot replicate. Rome built fast in part because Roman law allowed its generals to turn conquered populations into construction workers. I'm not going to skip past that to celebrate the arch proportions. But Vespasian's political calculation was also interesting beyond the raw economics of slave labor. He was the first emperor of the Flavian dynasty, a new man from an equestrian family who had seized power after the chaos of 68 to 69 AD, the year of the 4 emperors. He needed to establish legitimacy. So he took the land on which Nero had built his private pleasure palace. They drained the artificial lake Nero had installed there and put the world's largest public entertainment venue on the site. On land, Nero had stolen from the Roman people in a building funded by foreign conquest, free to attend for Roman citizens. Every architectural choice was a political message. The Colosseum opened in 80 AD with 100 days of games. Over 9,000 animals were killed in the inaugural spectacles. The message was received. I should add, and this is a detail I genuinely love, that the Colosseum's 80 numbered arched entrances at ground level were designed specifically to allow 50,000 to 80,000 spectators to find their seats and fill the stadium within minutes. The arches were marked with Roman numerals. You found your arch, but you went up the corresponding ramp or staircase to the correct seating level and section. The flow logic was so well designed that modern stadium architects still study it. The Romans invented efficient stadium crowd management in the 1st century AD, and many of the principles they used are still in operation in sports venues around the world. If you asked me to pick one Roman engineering achievement that best represents the full combination of technical sophistication, organizational scale, and sheer audacity that defined Roman construction, I would choose the aqueducts. Not the Colosseum, not the roads, the aqueducts. Here is why. Every other major Roman engineering achievement is impressive primarily for its scale, its speed, or its material properties. But the aqueducts are impressive for all of those things, and also for a precision requirement that would be demanding even with modern survey equipment, let alone with a wooden stick and a trough of water. By the late Empire, Rome, the city was served by 11 aqueducts totaling more than 250 miles in length. They delivered roughly 1,000 cubic meters of water into Rome every day, a per capita water supply that modern analysis suggests was roughly comparable to what New York City provides to its residents today. This was used for the famous public baths, for fountains throughout the city, for sewer flushing, and for private supply to wealthy households. The entire system ran on gravity alone. No pumps, no engines, no pressure vessels. Just the inexorable, reliable pull of Earth's gravity, as exploited with extraordinary precision. The Pont du Gard aqueduct, built to supply the Roman city of Nemours, which is modern Nimes in southern France, is the most spectacular surviving example, and it illustrates all of this perfectly. The spring source at Uzès was only 17 meters higher in elevation than the distribution basin in Nimes, 17 meters over 50 kilometers of terrain. Averaged out, that is a gradient of about 34 centimeters per kilometer. In some sections of the aqueduct, the gradient was as little as 1 in 20,000, meaning the channel fell 1 meter in elevation over 20 kilometers of horizontal distance. Near on the bridge itself, the three-tiered stone structure that is now a UNESCO World Heritage Site, the water channel at the top descends exactly 2.5 centimeters across 456 meters of bridge. That is a gradient of 1 in 18,241. 2.5 centimeters across the top of a 48-meter-tall stone bridge spanning a river gorge. And the surveyors who laid this out were working with a device called a chorobates, essentially a wooden bench with vertical legs, a groove cut into the top, and a series of plumb bobs. You poured water into the groove and used the water surface to establish a level reference. You could also use the plumb bobs if it was too windy for the water to sit still. That's the instrument, a wooden bench with water in it. And with this tool, the Roman surveyors maintained a gradient of 7 millimeters per 100 meters over 50 kilometers of winding terrain. For comparison, modern survey engineers achieve similar precision using electronic total stations with laser ranging and GPS correction. The Romans were doing it with water in a groove and a sighting line. One engineering analysis describes the precision they achieved as comparable to modern laser levels. I think that understates it. Modern laser levels are easy. What Rome achieved was hard, in a way that is difficult to fully appreciate unless you've tried to maintain a consistent gradient over a long distance with simple equipment. The blocks used to construct the Pont du Gard, some weighing up to 6 tons, were taken from a limestone quarry about 700 meters downstream from the bridge site. Each block was precisely cut to fit its assigned position in the structure. And I mean that literally. Each block was numbered at the quarry. the number designating its exact position in the finished bridge. This is prefabrication. Roman prefabrication, more than 2,000 years before the concept was named. The blocks were cut to dimension off-site, transported to the construction site, and assembled in order. No mortar was used in the main structural elements. The stones were shaped so accurately that they held each other in place through gravity and friction alone. The entire Pont du Gard bridge was completed in under 5 years. The full 50-kilometer aqueduct system took 10 to 15 years to build under the emperors Claudius and Nero, and the water channel was coated internally with a hydraulic plaster that incorporated crushed terracotta, then finished with a layer of lime slurry mixed with pork grease and the juice of unripe figs, a coating that both waterproofed the channel and reduced friction, maintaining a consistent flow velocity from source to city. That journey, from the spring at Uzès to the distribution basin in Nîmes, took approximately 27 hours. Through 50 kilometers of channel, much of it underground, across a 48-meter bridge over a river gorge, descending 17 meters in total elevation. Gravity-driven, continuous. And when the water arrived at Nîmes, it fed a city of 50,000 people. Here is what I find most astonishing about all of this. The full aqueduct runs underground for 35 of its 50 kilometers. What we call the Pont du Gard, the magnificent 3-tiered stone bridge that people travel from around the world to photograph, is just one spectacular piece of a much larger system that is mostly invisible, buried under the southern French countryside. The part that gets the tourists and the UNESCO designation is the tip of the engineering iceberg. Rome built the whole iceberg. And if you want to understand why, if you want to understand the philosophical and political orientation that drove this kind of investment in infrastructure, consider this. The Romans understood that supplying clean water to a city of 50,000 people was not a luxury. It was what made the city Roman. The infrastructure was the identity. The aqueducts were not just engineering. They were a statement about what civilization was supposed to look like. And now, if you're finding this as fascinating as I am, and you haven't subscribed yet, this is the kind of content we make on this channel. Ancient military engineering, the mechanics of empire, the technical details behind the history most people just skim past. Hit subscribe so you don't miss what's coming next. Back to Rome. You've heard the phrase, all roads lead to Rome. You probably know it's a metaphor for centralized power. What you may not fully appreciate is how literally true it was, and what an extraordinary engineering achievement made it possible. At the peak of the Roman Empire, the road network comprised roughly 400,000 kilometers of roads. Of those, more than 80,000 kilometers were stone-paved to the full Roman military standard, a construction specification that produced roads capable of carrying heavy military traffic in any weather, remaining functional for over a millennium after they were built. The Appian Way, begun in 312 BC and considered the first great Roman road, connected Rome to Capua, 132 miles away. Sections of it are still used today. 29 major military highways radiated from Rome itself. Emperor Augustus placed a Miliarium Aureum, a golden milestone, in the Roman Forum, inscribed with the distances to every city gate in the empire. This wasn't ceremonial excess. It was a logistical reference point, the geodetic center of the known world from which every distance in the empire was measured. What a Roman road began with a survey. The engineers, called agrimensores, used the groma, a surveying instrument consisting of a vertical staff with a horizontal crossarm from which 4 plumb bobs hung. By sighting along 2 plumb lines simultaneously, a surveyor could project a straight line over miles of terrain with remarkable accuracy. Britain's Fosse Way, A Roman road running about 180 miles deviates only a few miles from a perfectly straight alignment over its entire length. After the survey, the construction sequence was standardized. Dig a trench down to bedrock or firm subsoil, typically about 3 feet deep. Lay a foundation of large stones. Add a layer of crushed rubble, sometimes set in lime mortar. Then a layer of concrete or packed gravel. Then the surface. Tightly fitted stone blocks, but often of volcanic basalt in Italy, granite in other regions, selected for hardness and durability. The whole road was crowned slightly in cross-section, meaning the center was slightly higher than the edges, so rainwater drained off to the sides rather than pooling on the surface. Drainage ditches ran along both sides. The result was a road that could carry military traffic through Italian winters, British mud, North African sand, and Syrian desert without significant degradation. Many roads went centuries between major repairs. Some required only minor maintenance for over 1,000 years. A Roman legion could march 20 to 25 miles per day on these roads, in any weather conditions that permitted movement at all. This was not ordinary. Armies moving on unpaved ground might manage 10 to 15 miles on a good day. As the roads nearly doubled Rome's operational tempo, the rate at which military force could be projected across the empire. Roman commanders could calculate movement times with genuine precision. The journey from Cologne to Rome, 67 days by road. From Rome to the eastern city of Brindisi, 57 days. From Rome to Syria, including 2 days of sea crossing, 124 days. These weren't estimates. They were operational planning constants, reliable enough to schedule supply deliveries, reinforcement arrivals, and coordinated multi-axis military operations. Imperial couriers using the cursus publicus, the state post system, moved even faster. At the relay horse stations, called mutationes, positioned every 10 miles along major roads, couriers could exchange their tired horses for fresh mounts. Were using this system, official dispatches could travel 60 miles in a single day. Urgent news from a distant frontier crisis could reach Rome in days rather than weeks. This speed of communication and troop movement compressed the empire geographically in a way that made it governable. The roads were not just transportation infrastructure. They were the physical mechanism of imperial control, and they outlasted the empire by centuries. When Rome fell in the west in 476 AD, the roads didn't stop working. Medieval European commerce ran on Roman roads for 1,000 years after the empire that built them had collapsed. Many modern European highways follow the same alignments the Roman engineers chose 17 or 20 centuries ago, because the Romans surveyed the straightest, flattest, most practical routes. And the logic of their choices has never been improved upon. Let's go back to Caesar and the Rhine, because now that you have context for how Rome built, the story lands differently. In 55 BC, the Rhine River between what are now the German towns of Andernach and Neuwied was roughly 400 yards wide, ran up to 9 meters deep in places, and moved with a current strong enough to make conventional pile driving extremely difficult. The standard military solution for crossing a significant river, build a bridge of boats, using your fleet to create a pontoon crossing, was what every army did, and what Caesar explicitly rejected. He wrote in his Gallic war commentaries that crossing by boat he neither deemed sufficiently safe nor considered consistent with his own dignity or that of the Roman people. That's a fascinating statement. It wasn't just tactical, it was about what Rome was supposed to represent. Rome crossed the Rhine by building a bridge, because Rome built bridges. The design his engineers used had apparently never been attempted before. Pairs of 18-inch diameter timber piles were driven into the riverbed at an angle, leaning slightly against the current, not vertically, using drop hammer pile drivers mounted on rafts floating over the construction site. By angling the piles, the engineers used the river current itself as a reinforcing force. The harder the current pushed against the piles, the more firmly it pressed the angled members together into their driven positions. Upstream of the main piles, but diagonal brace members called defensores were driven obliquely to absorb the direct hydraulic impact of the current and debris. Downstream, additional braces stabilized against the back eddy turbulence. The whole structure was tied together with transoms, horizontal beams spanning between pile pairs, and decked with planking. Watchtowers went up on both banks. Barrier piles were driven upstream to deflect floating debris and potential enemy sabotage attempts. Caesar recorded in the Gallic War, "Within 10 days after the timber began to be collected, the whole work was completed, and the whole army led over." 10 days. For a bridge across the Rhine. The width of this bridge was roughly 23 to 30 feet, wide enough for legions to march in column. The length, based on modern estimates of the river at its likely crossing point, was somewhere between 460 and possibly over 1,000 feet. Even at the lower estimate, this was a bridge more than a football field and a half long, built across a major European river by soldiers with hand tools in 10 days. Caesar spent 18 days on the German side. He burned the villages of the Sugambri tribe, received submissions from allied tribes, then learned that the Suebi, the most feared Germanic confederation, were assembling in force deeper in the forests to the east. Rather than risk a battle that could undo everything he'd accomplished, Caesar withdrew across the Rhine and destroyed the bridge behind him. 2 years later, in 53 BC, he came back and built a second bridge. "In a few days," his account says. The second one went up faster than the first. It's because the engineers had now done this once and knew exactly how. The effect on the Germanic tribes was exactly what Caesar had calculated. For several centuries after these crossings, significant Germanic incursions across the Rhine essentially stopped. Not because Rome's legions couldn't be beaten in individual engagements. They could be, and sometimes were. But because the Rhine was no longer a military barrier from Rome's perspective. Caesar had demonstrated twice that when Rome wanted to cross the Rhine, it would simply build a bridge. That's not a river obstacle. That's a Roman road that happens to cross some water. The psychological dimension of Roman engineering is something I think historians sometimes underemphasize. It wasn't just about building things. It was about building things that demonstrated capability, dominance, and permanence in ways that conventional military force couldn't fully convey. The Rhine bridges were a message written in timber and iron-clamped pilings. The normal rules of geography do not apply to Rome. For a permanent bridge example, consider the one at Alcantara in Spain, built across the Tagus River and completed around 106 AD under Emperor Trajan. The arch stones, called voussoirs, weigh up to 8 tons each. They were cut to such precise tolerances that no mortar was needed in the joints. The stones are held in place by their geometry alone, each one pressing against its neighbors with calibrated precision. The bridge is still standing, nearly 2,000 years later. Still used. An inscription on the bridge reads, in Latin, "I have built a bridge which will last forever." The Roman engineer who wrote that was not wrong. At this point in this kind of video, there's usually a push to wrap up with something like, "And that's why the Romans were so amazing." But I want to spend a few minutes on a harder question, because I think the honest answer is more interesting than the celebratory one. Why, with everything we have, excavators, cranes, concrete pumps, computer-aided design, global supply chains, laser surveying, can't modern construction consistently beat Rome on projects of comparable scope? The short answer is that modern construction and Roman construction were optimized for completely different goals, and our optimization has costs that we rarely account for honestly. Rome optimized for permanence. Roman concrete was formulated to cure slowly and last millennia. But Roman roads were built with layers of carefully selected material designed to resist freeze-thaw cycles, heavy traffic, and flooding for centuries. Roman aqueducts were designed with redundancy, multiple aqueducts feeding Rome simultaneously, with bypass channels so any single aqueduct could be taken offline for maintenance while others continued operating. Roman bridges were built with stone tolerances so precise that they needed no mortar, because mortar can fail, but stone geometry doesn't. Modern construction optimizes for speed to function. Portland cement reaches working strength in 28 days because construction loans charge daily interest, and the developer needs the building occupied as fast as possible. Modern concrete uses steel rebar because it reaches strength faster than any alternative, and even though the rebar will eventually corrode and crack the concrete from the inside. Modern seawalls are built to a 50-year design life, because that's what the budget allows, even though Roman harbor structures built 2,000 years ago are still standing in the same seawater. The math on which approach is more efficient over a long enough time horizon is uncomfortable for the modern side. A Roman road that needs minimal maintenance for 1,000 years and is then still functional enough to serve as a foundation for a modern highway is, in pure life cycle cost terms, a vastly better investment than a modern road that needs resurfacing every 20 years. We just don't do life cycle accounting over a 1,000-year horizon because no modern institution, government, corporation, pension fund, plans on that timescale. There is also the institutional knowledge problem, and this one, I think, is genuinely tragic. The accumulated empirical engineering knowledge that Rome built over 5 centuries, the concrete formulations refined through generations of trial and error, the aqueduct gradient calculation methods, the arch proportion systems, the military engineering procedures that could be deployed anywhere the legions went. This knowledge was systematically documented, most notably by Vitruvius in De Architectura around 25 BC. It was written down. It was the engineering manual of the ancient world. When the Western Roman Empire collapsed in the 5th century AD, the institutional structures that maintained and transmitted this knowledge collapsed with it. The legions stopped building. The aqueducts stopped being maintained. Or the roads still worked for a while because you don't have to understand how to build a Roman road to walk on one. But the knowledge of how to build them, refine them, extend them, that faded within a few generations. The engineering achievements of Rome were not surpassed in Europe for approximately 1,000 years after the empire fell. Brunelleschi's dome in Florence, completed in 1436, was the first dome that exceeded the Pantheon's span in over 13 centuries, and Brunelleschi spent years studying the Pantheon before he figured out how to do it. In several specific domains, particularly marine concrete, Rome's achievements have genuinely never been surpassed. That knowledge gap is what Admir Masik's team at MIT was closing with their 2023 work on Roman concrete. For 2,000 years, and we knew that Roman marine concrete was extraordinarily durable. We didn't fully understand why until a group of researchers with modern materials analysis equipment sat down and worked through the chemistry that a Roman engineer empirically discovered sometime in the 2nd or 3rd century BC. Think about what that means. The self-healing lime-clast system, the seawater tobermorite reinforcement mechanism. The hot mixing technique produces both faster initial curing and longer-term durability. Roman engineers developed all of this through observation and experiment, refined it over centuries, and embedded it in a construction system deployed across an empire. Modern science, with all of its analytical tools, only decoded the full mechanism within the last 2 years. This is why the construction speed question is ultimately the wrong frame. The Romans didn't build fast by ignoring quality or durability. They built fast by achieving a level of organizational integration and materials knowledge that let them execute quickly without compromising permanence. The Caesar-Rhine Bridge, 10 days, 18 days of use, then deliberately demolished, was built fast because Rome could build it fast. The Pont du Gard, built over years, with precision that modern engineers find astonishing, was built at the pace it required to achieve the accuracy it needed. The Pantheon, 1900 years old, still the world record, still open to visitors, was built over the course of Hadrian's reign with no apparent rush, because permanence was the objective. But the machine behind all of it was the same: standardized materials, military labor discipline, state-level logistics authority, centuries of accumulated empirical knowledge, and the political will of emperors who understood that infrastructure was empire. That combination, not a single invention, not a single technique, but a system, is what made Rome's engineers capable of things that still require explanation. And the lesson for us, if there is one, is that the way we've structured modern construction, optimizing for speed, for quarterly cost accounting, for minimum viable strength materials that can be deployed fast, has real costs that show up over a long enough time horizon. Our seawalls are failing in the same oceans where Roman harbor concrete is getting stronger. Our highways need resurfacing that Roman roads didn't require for centuries. Our domes need steel reinforcement that the Pantheon has managed without for 2 millennia. We have better machines. We don't always have better outcomes. Let me bring this back to where we started. 55 BC, the Rhine River. Caesar's engineers looking at 400 yards of deep, fast-moving water, and 10 days later walking an army across it. That story works as a cold open because it's viscerally impressive. The speed, the scale, the audacity of the thing. But now that you've spent the last hour inside the Roman engineering system, I hope it lands differently. The Rhine Bridge wasn't a miracle. It was the expected output of a machine built to produce exactly that kind of result. An army that was also a construction corps, or a concrete formulation that healed itself, a dome built without steel reinforcement that is still the largest of its kind after 19 centuries. Roads that doubled the operational tempo of the ancient world's most effective military. A 50-kilometer aqueduct maintaining a 7 millimeter per 100-meter gradient using a wooden bench with water in it. None of this is magical. All of it is the result of a civilization that took engineering seriously at every level, materially, organizationally, politically, and philosophically. Rome built things to last because Rome believed that lasting things were worth building. The infrastructure was the identity. The monuments were the message. And the most haunting aspect of all of it, the part I keep coming back to, is the knowledge gap. The fact that after Rome fell, it took Europe roughly 1,000 years to approach Roman engineering capability again. Not because the buildings disappeared, many of them were still standing, obviously, but because the system that produced them disappeared. The institutional knowledge, the training culture, and the political will to invest in permanent infrastructure. All of it evaporated with the empire. We are only now, in the last decade, beginning to fully decode what Roman concrete actually was at the molecular level. 2,000 years after it was invented. There's something both humbling and galvanizing about that. Humbling because it suggests that civilization can lose things, real, valuable, hard-won things, and not recover them for a very long time. And galvanizing because it suggests that what the Romans discovered through empirical refinement over centuries is genuinely recoverable through modern materials science, and potentially applicable to the coastal infrastructure crisis that climate change is accelerating right now. The MIT research team isn't doing this for historical curiosity. They're doing it because modern seawall concrete fails in 50 years in the same seawater where Roman harbor concrete is still standing. the ancient solution may be the best answer to a very modern problem. If this video has done one thing, I hope it's moved the Pantheon, the Colosseum, the Pont du Gard, and Caesar's Rhine Bridge from impressive old stuff to evidence of a coherent engineering philosophy that we would do well to understand. The Romans were not smarter than us. They didn't have access to the knowledge we don't have. They had a system, and they ran it for 500 years, and the results are still standing in southern France, Rome, Spain, and along the former frontiers of an empire that has been gone for 15 centuries. That's the standard. Now you know what it looks like. If this kind of history, the mechanics behind the monuments, the engineering inside the empire, is what you're here for, hit the like button. It takes 2 seconds, and it genuinely matters for how this channel reaches the people who'd appreciate it. And subscribe if you haven't already. We cover ancient and medieval military history with the level of technical detail that the subject deserves. Byzantine defensive systems, what the Ottoman army's organizational model looked like and why it was so effective, how medieval siege engineers actually worked, the logistics and material science behind the great campaigns. There's a lot more coming. Leave a comment below. What surprised you most in this video? The self-healing concrete? The Rhine Bridge timeline? The Pont du Gard gradient? The MIT 2023 research? I read every comment, and I use them to calibrate what this channel covers next. We'll see you in the next one.